All right, hello everybody. Thanks for coming back to our second session on process level diagnostics and evaluation metrics. I want to note that our fourth speaker, this is here, Coumba Niang, is not here, so we have a gap at the 4:15 time period. So I think we're just going to move everybody up. That's okay. Also means that that can be a little bit more lax for the time. So there's not to be quite so nervous about the time limit and have time for questions. But other than that, we'll proceed according to the schedule. And our first speaker of this session is Charlotte DeMott. Please take it away.
Okay, thank you. I'm going to be talking to you today about some assessments of equatorial westerly wind events along the equatorial Pacific and the ocean Kelvin wave response to those wind events in the UFS-based prototype 8 or P8 modeling system. This is work that I've been doing with CSU colleagues Emily Riley-Del Ripa and Jingshan Choi, who is here in the audience. And a few months ago, we were introduced to Sulagna Ray, who is also at this workshop and has been working on these diagnostics. And so we've been meeting about once a month to try to explore some of these questions. And so what I'm showing you here in this figure is a vertical cross-section along the equatorial Pacific showing the stability profile, or the n-squared. And you can see, of course, this maximizes near the thermocline, and you can see the beginnings of an equatorial Kelvin wave propagating along the thermocline here. Jingshan has animations of these events if you'd like to see a nice illustration of that. But just to give it a little bit of background here, westerly wind events, or WWEs, and ocean Kelvin waves. So let's see. All right. In the Western Pacific, in the warm pool, so I'm showing the warm pool edge is indicated by the 28.5 degrees C isotherm, shown in magenta contours. This is about 10 or 11 years worth of observations. All of these yellow circles here are centroids of westerly wind bursts, or westerly wind events. The shading that you see in this diagram are sea surface height anomalies, which pick out the Kelvin wave propagation, and you can draw a line from the center of each of these westerly wind bursts, and they often line up with a ocean Kelvin wave that has been forced. And so this plot is based on observational data. And so what we wanted to know is how well are these processes, both the westerly wind bursts and the ocean Kelvin waves, represented in the P8 forecast system. And this is important because the westerly wind bursts, the Kelvin waves, the zonal currents that are forced by the wind bursts, these all take place, or these all participate in some of the zonal migration and eastward expansion of the warm pool, which has been associated with both the onset and the maintenance of El Nino conditions. And before I go farther, previous work, including some done by our group, but also others shown here, have indicated that the majority of westerly wind events that are strong enough to excite an ocean Kelvin wave are associated with the Madden Julian oscillation. Some are also associated with convectively coupled equatorial Rossby waves in the atmosphere. So these westerly wind bursts tend to be associated with large-scale organized convective systems. So when we ask how well does the model simulate these events, you can think of it both in terms of the forcing, the westerly wind event, and the ocean Kelvin wave, which is the response. So on the top here, I've drawn sort of a downward-looking view at XY cross-section along the equator. Down here is a longitude depth illustration, and this is just a little cartoon to show you what we'll be looking at. If you have a westerly wind event that originates in the atmosphere, this forces the upper ocean with a wind stress. This wind stress can then excite a zonal surface current along the equator, and through Ekman transport, you get an increase in your sea surface height. And so this looks like a raising of the sea surface height here along the surface, but a suppression of the thermocline below as this. And then this Kelvin wave can propagate freely even after the wind forcing has ceased. And so Jing Xuan and Emily and I are funded by the NOAA MAP program to develop some diagnostics that we've applied to CMIP 6 model output. And sort of the goal of this project has been, can we adapt some of these diagnostics to better understand these processes in the P8? And so just a reminder, I think most people in this room are aware of this. The P8 forecast, we're looking at a retrospective forecast period. We have 35-day deterministic forecasts. The period spans April 2011 to 2018. Forecasts are initialized on the 1st and 15th of every month. So this 7-year reforecast period yields a total of 168 forecasts. And as I mentioned previously, these westerly wind bursts are often associated with the MJO. And I just wanted to point out that the P8 shown in these curves to the right tends to have improved MJO forecast skill compared to earlier prototypes of this model. So this gives us some confidence that the model should at least be able to predict the westerly wind events that drive these ocean responses. So when we develop these diagnostics from the CMIP 6 model output, we're looking at long time series of surface stress along the equatorial Pacific. And so we can filter the surface stress, and then we pick out events. This is following an algorithm from the Puyadal 2016 paper, where we identify surface stress anomalies greater than 0.04 newtons per square meter. This is roughly a 2 sigma threshold. They must last at least 5 days and extend at least 10 degrees in longitude. This is a fairly commonly applied threshold for similar studies. And then we can compile statistics on westerly wind events, such as their zonal extent, duration, their integrated wind work, if you add up the surface stress within this patch, and their centroid. Now, because we're dealing with 35-day forecasts, we can't do a long bandpass filter, but what we found works reasonably well is to, well, first of all, let me say, of the 168 forecasts available, we said for our initial analysis, we wanted to pick out forecasts that were initialized during an active westerly wind burst event. So we didn't want to, this just simplifies the analysis. How well can the model sustain that westerly wind burst? And then how does the ocean respond to it? So 7 years, 168 forecasts. It's a little sad that we only got 11 events, but we're gonna go with this. And from those 35-day forecasts, we're looking at the anomalies with respect to the lead dependent climatology. And then we also subtract the 35-day mean anomaly from each forecast to remove the background state. And so what we're left with is something that looks similar to this plot on the upper left. And what I'm showing you here is a comparison of just 4 of these events. As depicted in the Era 5, this is surface stress for 4 events and the corresponding events from the P8. And when we saw these plots, we just visually, we thought the model seems to be doing a pretty good job. So this was encouraging. So you have the strongest westerly wind events here, for example, at the initialization date. The westerly wind event later dries out. For example, in this case, the model does a pretty good job. But in order to quantify this, our first attempt at this has just been to say, well, what is the pattern correlation of the surface stress anomalies in this body? So this is like 1 week. So the first week we have, we can calculate the pattern correlation skill for each event in each week. So we just march our window up and we get skill assessment over 5 weeks for all 11 events. And so the results of this analysis are shown here, where each of the thin curves are the pattern correlation skill as a function of week. for each individual event. And then the mean skill is this thick, magenta line here. And so I don't think it's too surprising. We see that the skill is largest early on in the forecast, and then it degrades some. It does remain positive. I'll just say, we think there may be better ways for us to assess this skill, but these are still just kind of ideas rumbling around in our heads now. So we may work on that. We did wonder if the skill would be higher for these westerly wind events, since we assume they are associated with large-scale organized convective systems that may persist farther into the future than forecasts that were initialized during non-westerly wind event periods. But we find that the skill, at least using the measure that I just showed you, does not vary tremendously between the 11 westerly wind events shown in black and all forecasts that are initiated. So this kind of concludes our analysis of these 11 westerly wind events, and now we turn our attention to the ocean Kelvin wave response. So this is the ocean sea surface height anomaly for the same 4 events that I showed you in the previous slide for the surface stress. We have observations in the top row, and so you can see for each westerly wind event, you can clearly see evidence of Kelvin waves in these events. So the Kelvin waves that are being driven by the westerly wind event. And these are the results for the P8. And you can see that there's definitely some correlation there. The model is producing Kelvin waves. We remain a little bit puzzled by what appears to be an excess of what we think is inertia gravity wave features in the P8. We don't know why this might be. It seems like a fairly robust feature. But if we take all of these Kelvin wave events and we shuffle them so to a common longitude, the longitude where the westerly wind burst event is located at the first forecast day, we can make a composite of them, which is shown here. So this is a composite of the observed and the modeled Kelvin waves. So they have very similar propagation speeds, which is a good thing. We do not necessarily see this in the CNIP6 models we've analyzed. In those models, the Kelvin waves tend to propagate a little bit too slowly. So the phase speed of the Kelvin wave in the P8 appears to be well simulated. But we are, and just to show you this is the skill score. It's relatively flat with lead time. The Kelvin waves are obviously a much lower frequency phenomena than the wind burst forcing, so we don't really expect, it's not too surprising that the skill is sustained throughout this forecast period. But the other things we want to ask was, well, what about the Kelvin wave amplitude? And so to do that, we can take the mean amplitude along this wavefront for each event. I'm just showing it for the composite here. And we can ask, well, how sensitive is the Kelvin wave amplitude for each of these events to things like the stability of the thermocline or the strength of the wind forcing? Okay, that's the question. I was trying to remember if that just showed up there. So, okay, you can see most of these colors. So here we've taken the Kelvin wave amplitude for each of these 11 events, and we average along its wavefront, and we correlate it to the mean stability of the thermocline for each individual wave event. And you can see that for the 11 events analyzed, the correlation is about 0.45. So for 11 events, this is not statistically significant at 95% level, closer to maybe 90%. And when we do a similar analysis for the integrated wind work, which is the sum of the wind stress over each of our western wind event patches that we've identified, we see a similar correlation, 0.47, so almost the same as what we see here. And Jingxuan has also done a similar analysis for the CNIP6 models and observations. For observations, we find that the sea surface height anomalies are more strongly correlated or more highly correlated with the integrated wind work rather than the thermocline stability. Although the models are not quite as strongly correlated as they are in the observations. So this is all a little bit first look that we're doing so far. Like I say, we are trying to come up with maybe a better way to assess the skill of the westerly wind events. I'm getting ahead of myself, but so just to summarize, the first point is that the analysis of the P8 performance is really aided by the availability of daily ocean output. It's almost impossible to do this analysis in more than just a handful of CMIP 6 models because daily ocean output beyond SST is generally not available. The P8 is great because we can get vertically resolved daily output, numerous two-dimensional fields that can help us really understand the model behavior. So it's a very attractive data set for exploring some of these questions. And so initially, even though we've really only looked at a few case studies, the P8 appears to well simulate the general features of the westerly wind events. It has a robust Kelvin wave response. We remain a little bit curious about the westward propagating features embedded here. And we're not finished. One thing we're very interested in looking at in the future is the role of ocean barrier layers in these processes. So where we have salinity and temperature stratification that occur at different depths along the equator, that can be very effective at trapping momentum fluxes near the surface and perhaps enhancing the zonal currents that develop in response to the wind forcing. Yeah, I would like to sort of figure out a way to look at more westerly wind event cases in the P8. And this may involve looking at westerly wind events that develop within the model that don't necessarily develop in the real world. This can be one way for us to increase our sample size. We hope to publish these findings soon. Like I say, these diagnostics have been developed for climate-linked simulations. Whether or not it's something that we could formally develop for forecast model output, I think remains to be seen. But this type of analysis does give us some sort of background knowledge or familiarity with this modeling system, which could potentially be helpful for the upcoming TPEX field campaign, which will be held in 2026 to 2027 timeframe along the Equatorial Pacific. One focus area of which is the eastern edge of the warm pool, where we want to examine processes that lead to zonal shifts in the warm pool edge and the response of convection to those shifts. So that is pretty much all I have. So I'm available for questions if there's time.
Anyone have any questions?
Charlotte, the events that you picked seems to be ENSO years, most of them 2014 and 2015 to 2016. These are the two El Nino events.
So the four I showed, I think these are the full 11. Yeah, I'm seeing about a 2015 in there.
If I remember correctly, these are the MJO events that are initialized that are in the initial condition in this period.
They should be in the, they should appear in the initial condition.
Yeah, there are about 11 MJO events, and then these are ENSO events.
They could be, and
They are, I mean,
yeah,
yes.
yes.
So it might be that's just if you have if you have an ENSO event, you do have some Kelvin wave
Yeah, so you definitely do get more of these westerly wind events that, especially that propagate farther eastward during El Nino events. I mean, I won't go back to it now, but in the 10-year time series I showed, you do see these westerly wind events that occur in all years, but they are definitely more frequent during El Nino events. And it happened maybe, they just happen more on the 1st and 15th of the month when we can't really look too far beyond that. If we wanted to ensure that the model was initialized with an active westerly wind burst.
Yeah, so I wonder if, if you look at the westerly wind bursts generated by the model on its own, if that will look.
That would, yeah, so there are many, yeah, let me just show you, there are certainly opportunities to do that because the model does tend to produce its own westerly wind bursts that are often like very beautiful canonical looking westerly wind burst events. They don't have a observational partner, but it's still a westerly wind event. So, it happens, and we don't know if this is something that happens all the time or if it's just shows up in these two cases, but that would definitely be a good way to look at the ocean response.
Yeah, I know that for these particular years, for ENSO years, there is a very good, the model does a very good job in representing the interaction between the wind stress and the Kelvin waves for these two ENSO.
For those events.
Yeah, so that's
Okay.
the reason I am asking. Outside of this, you can see such a good.
Yeah, I think it's actually, there's a case to be made for looking at these other events. Just to look at the response, ocean response. Yeah. So, all right, thank you.
Thank you, Charlotte. Thank you. We'll now move on to our next speaker, is Brandon Wolding.
Cool. Yeah, thanks for the opportunity to speak today. This is work being done by a big team of us at NOAA PSL, being led by Vijit Methil, who's a postdoc within our group, looking to towards improving tropical convective coupling and air-sea interactions in the UFS. Oh, look at the screen here. So yeah, everybody here is aware of how important the tropics are for predictability on subseasonal to seasonal timescales. And we've heard a lot today about how rapidly our subseasonal to seasonal forecasts can degrade. This is a figure from Gaina et al. 2022, showing the coherence squared between precipitation and 850 hectopascal convergence. So essentially a measure of the coupling between convection and large-scale circulations for ERA 5 on the left, GFS version 16 forecast hour 6 in the center, and then on the right is the change in coherence squared that occurs between forecast hour 6 and forecast hour 48. So what you can see is that forecast hour 6, this coupling between convection and large-scale circulation is pretty well represented, but most of this is lost within the first 48 hours of the forecast. This is something you can see if you just look at Hofmoller's of precipitation. In observations, you've got these nice eastward propagating precipitation bands associated with Kelvin waves, which are pretty well represented at these 12-hour lead times. But if you go out to 5 days, you see a lot of that eastward propagating variability has been lost. Our seasonal forecasts can also degrade rapidly. These are a couple figures from work by John Beverly, Matt Newman, and Andy Hoyle that was published last year, looking at ENSO-related SST errors in seasonal forecast models. I want to draw your attention to the figure on the right here, which shows forecast errors for a single October initialization. The forecast errors in SST are shown in the red contours, winds in the vectors, and precipitation in the colors. And what I really want you to note is just that these forecast errors associated with this westward extension or shift, which is really consistently seen across models, develops really rapidly within the first 5 days. So the goal of our work is to use process level diagnostics of convective coupling and air-sea interactions to better understand what's driving this rapid development of forecast errors and biases. Specifically, we're going to be assessing the relationship between 4 variables: precipitation, moist static energy, which is basically a measure of column water vapor, upper ocean heat content, and then a measure of convective instability known as lower tropospheric buoyancy. I'll just refer to that as buoyancy as short. And today, for the sake of time, I'm just going to focus on the convective coupling part of this work, and we're going to talk about the relationship between precipitation and buoyancy. So our research questions. Number one, does model convection respond to the large-scale thermodynamic environment in a realistic way? Number two, does model convection in turn impact its thermodynamic environment in a realistic way? And then how do these biases develop with forecast lead time? So we're looking at a range of different simulations which allow us to basically examine how these model errors or biases accumulate over time scales from hours to days and weeks to years. So on the short end of that time scale, we're looking at the UFS replay. This is a simulation where winds, temperature, specific humidity are essentially nudged towards AR5. This is done with the UFS HR1 coupled prototype. And then on the far other side of the spectrum, we're looking at a free-running UFS climate simulation using the UFS version 17 prototype 8 with stochastic physics. And between these two, we've got our uncoupled S2S reforecasts, and that's using the GEFS version 12, which is the current operational system. So just to highlight, reforecasts are using GEFS version 12 versus the replay and the climate simulations are using different prototype model versions that are at different stages along this developmental chain towards SFS version 1. And then I want to take just 1 minute to introduce this measure of convective instability that we're using. So lower tropospheric buoyancy, you can basically think about this as like a fancy parcel calculation. So we initialize a plume, i.e. a parcel at 1,000 hectopascals using temperature and moisture profiles. We then allow our plume to rise, i.e. we lift our parcel. And as the plume rises, we allow it to mix with or entrain surrounding environmental air. So we get to decide what those entrainment profiles are. And in this case, we've used what's known as a deep inflow B entrainment profile. And that just means that the plume is going to mix with its surrounding environment over a deep layer of the lower troposphere. And then what the plume model outputs here are virtual temperature estimates of the plume, which can be compared to the virtual temperature of the environment. The difference between those two is a measure of buoyancy, which we're going to integrate in the vertical. So the way to think about this is really just as a coarse estimate of the ability of the large-scale environment to support deep convection, but one that takes into consideration the vertical structure, vertical stratification of moisture and temperature. So a little bit more sophisticated than a measure like column saturation fraction or your traditional non-entraining CAPE measures. Okay, so let's look at some results. So first question, does convection respond to buoyancy in a realistic way? In this figure, we've got AR5 buoyancy on the x-axis. So dry and stable environments are on the left, moist and unstable environments are on the right. Our y-axis is I-merge precipitation rate. The black solid line here shows you the bin mean precipitation rate. So when buoyancy is really low, we've got no precipitation. And then as buoyancy increases beyond what's often termed a critical point or a critical threshold, we get this really rapid pickup of precipitation with increasing buoyancy. Now the black dashed line here, that shows the PDF or the distribution of this measure of buoyancy, which you can see has this really long tail off to the left of the critical point and then drops off really rapidly to the right of the critical point. So one interpretation of the shape of this PDF is that this long tail is the result of large-scale processes. So think like surface fluxes of heat and moisture, radiative cooling aloft, these large-scale processes slowly driving the atmosphere towards instability. Then once we get past the critical point, we get this transition to deep convection. You get the rapid removal of buoyancy by convection. And these two processes are pushing towards each other and come into some sort of semi or quasi or statistical balance here near the critical point, which is where we see the mode of the PDF or the most frequently observed state of the system. So let's look at UFS climate simulations. In UFS climate simulation, we see a precipitation begins to pick up earlier than what we see in observations. And then here at these more extreme precipitation rates, precipitation is being underestimated. If we change the y-axis to a log scale, allowing us to focus on precipitation rates less than 1 millimeter per day, we see this really common drizzle bias down here, though I-merge might not be the best measure of this because it doesn't capture light and shallow precipitation that well. So we're going to focus on these other biases a little bit more here. So if we look at UFS replay, the one that's continually nudged towards ERA 5, we see a similar too early precipitation pickup and then underestimation of these higher precipitation rates. And the same thing in GEF's forecast day 1. So to get a little bit more information on what's going on here, we're going to look at these precipitation biases as a function of both ERA 5 buoyancy and I-merge precipitation rates. We're just going to bin our data by both our X and Y axes here. And we can see that we tend to precipitate too much, specifically in this regime where it's really unstable and we've got moderate precipitation rates between 1 and 10 millimeters per day. And then we tend to underestimate these more extreme precipitation rates greater than 10 millimeters per day. And we can learn even more information about this by looking at CloudSat cloud types. So we examine CloudSat cloud types, and 2 cloud populations really match up well with this. The regime in which we tend to over-predict precipitation matches up with congestus clouds in the transition to deep convection. And where we tend to under-forecast precipitation is associated with our mesoscale convective systems. We see this in replay. We also see this in our GEF's day 1 forecasts. Now, moving on to our second question, does convection impact the thermodynamic environment in a realistic way? Well, unsurprisingly, if you get this transition towards deep convection earlier on, that ends up driving you towards a more stable climate. This is the UFS climate simulation. We can see that it's kind of critical point here. Mode of the distribution has been shifted to a more stable climate. And we see a similar thing if we look at GEFs in magenta here at forecast day 1, and also notably in this replay simulation. So replay is ending up too stable despite having these continual increments added to nudge it towards ERA 5. So those increments are being very rapidly consumed in that simulation. We can learn more about these buoyancy biases or stable biases by looking at this as a function of both ERA 5 buoyancy and I-merge precipitation. And basically, we're just seeing the rapid stabilization of these most unstable environments. And if we look at the vertical structure of this, so in this case, I'm looking at the replay moisture increments integrated below the freezing level in this bottom plot, and then above the freezing level in this top plot, we see that replay is continually having to add moisture below the freezing level and take moisture away above the freezing level. So we've got this moistening, drying dipole, which is not super evident if you look at column integrated measures of water, like column saturation fraction. If we look at the GEF's day 1 forecast bias, which is the solid line, and day 3 forecast bias, which is the dashed line for specific humidity, we see the same dipole here, and we can see that most of this bias develops here within the first day of the forecast and then strengthens a little bit between day 1 and day 3, but same consistent moistening, drying dipole around the freezing level. So with the last couple of minutes I have here, I just want to talk briefly about the covariability between precipitation and buoyancy and the important role of entrainment. So with this plume calculation, we can run this model a couple different times using different entrainment profiles. In this case, we turned entrainment off, and then we turned entrainment on using this deep inflow B profile. In the top figure here, I'm showing non-entraining buoyancy. So this is a buoyancy calculation, no entrainment, and the coherence squared with the observed I-merge precipitation, which you can see is very low. So that's just to say that a non-entraining measure of buoyancy is not a very good proxy for convection in the tropics. If instead we use this deep inflow B profile to calculate our buoyancy, we can see that our coherence squared is really high, in excess of 0.55, 0.6, which is to say entraining measures of buoyancy are much better proxies for convection in the tropics, which we've known for quite a while. So how are our models doing? Well, looking at UFS version 17 prototype 8, you can see that it's getting the ratio between these two roughly correct. It maybe has a little bit too much coherence with this non-entraining measure of buoyancy, and we like to see the coherence with this entraining measure of buoyancy maybe be a little bit more red, but overall it's doing pretty good, especially when you compare it to something like E3SM version 2, which has incredibly high coherence with this non-entraining measure of buoyancy. So the developmental work on the convective scheme for UFS prototypes seems to be doing very well. So with that, I'll just conclude by saying the excessive precipitation that we're seeing specifically in this congestus regime in the transition to deep convection is, we've got this too early precipitation pickup, and this is driving a rapid stabilization of the climate with this moistening, drying dipole centered on the freezing level. This rapid stabilization is directly contributing then to the underestimation of the most extreme MCS precipitation rates, and these biases are developing very rapidly within the first 24 hours. So yeah, so thank you for the opportunity to speak, and I'm happy to answer any questions you may have.
Any questions? So thank you so much. So we will now move on to our next speaker, which is Timothy Eichler.
I don't know about buoyancy.
He has some extras. I couldn't take them.
I didn't study it.
There we go.
There we are. Here, thank you. So my name is Tim Eichler. I'm a contractor here at CPC. And I'm going to talk about a comparison of the Synoptic climatology of US MGO impacts in the ERA5 reanalysis data set and a GESS V12 model. Mostly to my ERA5, we started to do a little GESS V12 analysis. I'll show that as well. I'm working with Dr. Dylan Ellsbury over at NOAA CIRES. I said we'll have a great deal of fun doing this project. So questions I'm going to explore. What are the precipitation patterns for MGO phase that lead zero? Is there agreement among different data sets? Data sets I'm going to show are CPC unified gauge data and ERA5 data, which is daily. For MJO, I use RM1, RM2 daily data. I described in Wheeler and Herndon in 2004. Number two, can the GESS V12 model simulate MGO precipitation patterns that lead zero? The GESS V12 data is produced weekly from 1500 with 35 leads daily. And I'll say a lot of this work I'm going to show is based on a lot of the literature review I did. And I found some really fun results, and it kind of inspired my imagination. And I kind of expanded upon what I found in the literature. I'll show you that in a few different ways. Number three, regarding the lead times, Casal et al. 08 found relationships with the NAO for phase 6 with NAO negative and phase 3 for NAO positive leads greater than 10 days. Can this be discerned, for example, leads 13 days, which I'll explore. Now, Casal's work, what I like about this, and I'll show this as well, is that, when I look at NAO, NAO is noisy, it's atmospheric, it's day to day. If you look at a model, you look at it for a few days and then you lose predictability. But what Casal was able to show was that during specific MGO phases, namely 3 and 6, the NAO in phase 3 of MGO tends to go positive around day 7 to 8 and stay positive beyond that for at least a week. And for phase 6 does it for NAO negative. So I found that intriguing because here I am with something, if I'm standing here right now, I know what MGO state I'm in. But if I know what MGO state I'm in, I might have some information about what the NAO will do at interseasonal timescales. Number 4, if the MJO-NAO relationship is detected, does ENSO as a background state alter this relationship? And this also is based on some of the literature that I found. I'll go into that in a second. So motivation, once again, is there predictability in reanalysis and model data for the NAO in specific MJO phases and specific ENSO phases? And here's the roadmap I found. So this roadmap, this just shows where I went with the literature. So MGO's phases 3 and 6. Phase 3 tends to produce NAO positive, phase 6 NAO negative. That's Casal's work. I'm also going to show at lead zero, Arcodia et al. 2020. What's good about Arcodia's work is that she separates out ENSO and NAO. And so I kind of try to duplicate her work at lead zero. I'll show that initially in this talk. Next step will be then, okay, here's what Lee did. So Lee said, okay, here's Casal's work. It's interesting. Let me build on that. Now let's separate it out. Instead of just saying MJO versus NAO, let's do MJO El Nino, MJO La Nina, and do the same thing. And then if we went on, so I got as far as Lee. So Lee would show that phases 0, 1 to 5 MJO produces ENSO positive is NAO positive. And I should put this in here for phase 7. ENSO negative and positive produce an NAO negative for Lee. What we're going to get to, and this is something where Dylan has a lot of experience with, we're also going to eventually look at QBO, look at the West phase particularly. Feng and Lin in 2010 found out for MJO phase 3 with a QBO West, NAO tends to be positive. MJO in phase 7, QBO West, NAO tends to be negative. And if we went even further, what's another thing forecasters will look at? They'll look at, I'm a weather windy, I look weather maps every day. What's the NAO doing? What's PNA doing? So Sal and Lee found that in MJO phase 2, they found a relationship with PNA negative, and for phase 6, PNA positive. So right now, as far as we've gotten so far, we'll show some of the things with Casal, Arcodia, and Lee. We haven't gotten this far yet, but that's will be the next step for what we're doing. So here's some of Arcodia's work. So on the left, so this is precipitation composites by MJO phase. So phases 2 and 3, 4 and 5, 6 and 7, 8 and 1. Green indicates above normal precipitation, dry, and orange, red areas are below normal precipitation, dry zones. And she removed ENSO by removing the 120-day running mean. I did the same thing with the reanalysis data sets as well. I tried to match her as best I could. And you can see that during MJO phase 2 and 3, it tends to be wet in the West Coast and across the eastern part of the US. Phases 4 and 5, it dries out across the eastern part of the US. 6 and 7, you got wetness across the Midwest. And then for 8 and 1, you're back to wet along the East Coast, dry in the upper South. So I looked at 2 different data sets, CPC gauge and ERA5. You'll see some signal over the ocean of ERA5 because it allows me to. CPC gauges land only. So you see that it duplicates results pretty well. So wetness across the Southeast and the West Coast for phases 2 and 3. Not very clear here, but there's some hints of dryness across the eastern part of the US for CPC gauge and also for ERA5 for phases 4 and 5. The wetness shows up both for the gauge, not so much though for ERA5. I also like to show this because also there's sort of an assumption we all make, use one reanalysis data set, here's what it's showing. Sometimes the reanalysis data sets will give you different answers. So I learned from a reviewer a long time ago with one of my papers who pointed out, always show more than one reanalysis data set, so I try to do that whenever possible. And then phases 8 and 1, wet across the Southeast for the gauge data, also for the Southeast and off the East Coast for ERA5. I also want to note, I can't show it with Arcodia's work, but what I'm seeing too is that in ERA5 data, for phases 2 and 3, 4 and 5, it's dry in the Pacific. There's wetness, it's above normal precipitation for 6 and 7, 8 and 1. So part of looking at synoptic climatology, so what did I mean by that? I like to look at, things from the surface all the way to higher levels of the atmosphere. So I'm going to show you results from storm tracks, 500 millibar height data, and also 200 millibar wind data. So first, let me show you some storm track results. So I've done a lot of work with storm tracks, and I happen to have this data set just lying around, so I thought I'd just see if I could assess it for MJO. And the way I look at storm tracks is that the way you define a storm, at least for this, is that a storm is the lowest pressure in a grid box relative to surrounding grid boxes. So it's a surface-based, sea level pressure-based storm. And so once again, here's Arcodia's work, and here's ERA5. So notice this dry, dry, wet, wet. Well, storm frequency, this is ERA interim data. So I didn't have ERA5 data, so it's a bit of an apple and an orange, but it's some proxy that should be almost correct. So you're seeing a decrease in frequency in storms across the Pacific for 2, 3, and 4, and 5, an increase 6 and 7, 8, and 1. That's pretty consistent. You're also seeing this dryness across the Southeast in phases 4 and 5, a northward displaced storm track. The one thing I don't quite understand yet, and if one of these initial results, is why I see if I'm seeing more storms up here, why I'm not getting a rainfall signal up across the US-Canadian border or the North Atlantic. So something to check further. One thing I also have in my arsenal now of looking at data is I can also look at precipitation with the storms. That'll be the next thing I look at with this. And also for phases 8 and 1, you can also see that more storms across the eastern US, out across the Atlantic, and that matches this wet area off the East Coast. And by the way, these results are for NDJFMA, which is matches what I'm coding. So the next step then, so that was for lead 0. We're about for longer lead times. This goes into Casal's work. So here's the contingency table from Casal 2008. And so I looked at this is NAO positive. This is phase 3. Here's phase 6 down here. And what these orange squares indicate, more frequent NAO positive events during MGO phase 3. At lead time is down here. At lead time, as you start out with around day 6 and continue. So it's a persistent signal. So I thought I would look around day 13 or so. So I circled that area here. And this is day 6, right? This is rather MGO phase 6, NAO negative. So what Casal notes is that there's a slope. So you can see a slope from slightly negative to positive indicating that over time, you get to a certain MGO phase, the NAO tends to evolve in a certain way. And the orange bars indicate it's the NAO more frequent than climatology. So this would suggest that for phase 3, you tend to get NAO positive at lead times greater than about 7 days. For phase 6, NAO negative around, let's say about 6 or 7 days and beyond as well. So for kicks, I went back and said, let me look at went to the PSO website, one of the little things I play with sometimes. I'm going to correlate just precipitation with NAO. And his results, by the way, NDJFM, okay? So I'm going to do NDJFM correlation. So you're seeing these kind of banded structures, so negative correlation. So if I have a negative NAO, wet, dry, wet, wet, and dry. So that's the pattern I expect to get. So what I thought I would do is let's take this, this time series, this contingency plot. What would this look like two-dimensionally? So I took phase 6 for lead 12, NAO negative, and then phase 3, approximately for NAO positive. And I looked at guess V12, ERA 5, the CPC gauge. For V12, you're seeing some signal in the Pacific, but you don't really see much in the US. So the guess V12 doesn't do much for phase 6. The NAO negative signal doesn't really show up well, if at all. ERA 5 is seeing a tendency for wet across the east, that wet, dry, wet signal. CPC gauge, the same thing. Notice for phase 3, you get a kind of reversal, much more dryness across the eastern part of the US, which is more of a signal of a NAO positive. Interestingly, for the guess V12, you did get more signals. So although phase 6 didn't show much, phase 3 did seem to show an NAO positive signal, even in the guess V12 data. So let's go further then. So since we have this trend with the NAO, I thought I'd do a regression analysis of these different signals. So this is once again mimicking Casal's work. I did a regression over 13 days, from 0 lead to 13 days out, and of the 500 millibar data, which is the top, 200 millibar wind in the middle, precipitation at the bottom, and for kicks, the storm tracks in the bottom. And this is phase 3 on the left column, phase 6 on the right. So the shaded areas, the hatched areas indicate significance of 95% using a two-tailed t-test. So you're seeing that for phase 3, you're seeing this blue color up here, below normal heights, above normal heights, definitely a signature of an NAO positive. For phase 6, you're seeing it in reverse. 2 more of our winds. If I'm lowering heights up here, I expect to have stronger winds down in this area. Nicely consistent. Weaker winds here, consistent with blocking or higher pressure across Iceland with NAO negative. What I find really kind of interesting about this is that I'm not looking for NAO. If I was just looking at MGO, this would pop out. So this is kind of almost a fortuitous kind of result. It's not something you necessarily look for, but it's something you do see. Precipitation, if we're looking at evolution of precipitation for phase 3, drying across the eastern part of the US, consistent with NAO positive. A wet, dry signal here, very consistent also with NAO positive. NAO negative, just reverse everything. So it looks pretty good. I was actually kind of surprised to see it look this good. For the storm tracks, I decided for fun just to take storm tracks for phase 3 minus phase 6. And by the way, the amount of data for the I was looking at was from 1979 to 2016 for the storms here. So you're seeing a tendency for increased storms for phase 3 relative to phase 6 across the North Atlantic, proximate NAO positive phase. Even the Pacific, this pattern in here is also this negatives across northern Japan, North Pacific, positive southwesterly dilution, consistent with, I was just, instead of doing phase 3 minus phase 6, I took NAO positive minus NAO negative. It's what I expect to see. So then let's look at El Nino then. So El Nino, I took all the El Ninos from the CPC website and during that 79 to 16 period, and composited them and subtracted out all the, all the data to get this regression analysis. So if I would have more height data and phase 3, phase 6, once again, going back to the all data versus El Nino, very consistent. So if you're a forecaster and you're in, let's say you're in phase 3 or you're in phase 6, if you're in El Nino, it's the same signal. So in other words, I expect to get NAO positive for phase 3, NAO negative for phase 6, exactly what I get for the height data, the wind data, and the precipitation data, all consistent. However, if I go to La Nina, the signal kind of goes away. So for phase 6, all of a sudden, I recall, El Nino, I got this nice looking NAO negative signature in the height data. Well, if I go to La Nina for phase 6, I lose it. So you don't see this NAO negative signature anymore. So it seems that this kind of relationship only seems to work for El Nino states, not for La Nina states. So you see that for the height data. For phase 3, also you kind of lose it as well. So La Nina, you tend to lose it for this phase 3, phase 6. So let's look at what Lee said. Lee says, no, let's look at phase 7. So phase 7, he expects both for El Nino and La Nina NAO negative. And for El Nino phase 7, for the height data, indeed, you're seeing an increase in heights across Greenland, Iceland, decrease in heights in North Atlantic, consistent once again with a negative NAO. Interestingly, for the La Nina, I think the pattern is kind of ambiguous because this bottom part would be kind of consistent with a negative NAO, but the top part here is not. That's more consistent with a positive NAO. So to me, even here for phase 7 La Nina, it tends to be a bit muted. Perhaps, if I look at, his contingency table, so he took the South table, divided up by ENSO state, the El Nino frequency doesn't quite jump out as much as, let's say, this is NAO negative for El Nino, this is NAO negative for La Nina. It tends to be much more robust, it seems, for El Nino, and I seem to see that in the data as well. So where does this leave us then? So 79 to 17 composites are consistent with Arcodia et al. 2020. Casal OA found that MGO phase 3 is followed by a positive NAO. MGO phase 6 is followed by a negative NAO at interseasonal time scales, which is persistent. That's really what I found really interesting about this. Our initial analysis supports these changes in the synoptic climatology from 200 millibar winds all the way down to the storm tracks. Even without model support, forecasters should keep these relationships in mind given a known MGO phase. I don't need a model to tell me what the NO is going to do in 2 weeks. If I know the MGO right now, these are relationships that tend to happen. At least that's what the data show. Speaking of models, the GUSP 12 shows the MGO precipitation relationship, although less in magnitude than ERA5 CPC gauge, and once again, particularly for NAO positive as opposed to NAO negative. Resolution could be after model physics. It's really good paper by Feng et al. 2021, which goes into all the different models. One of the other possibilities is that what Feng et al. Said that NAO tends to be much better when the stratosphere is much better resolved. So vertical layers in the stratosphere could also play a key role. The ENSO results are interesting. El Nino is consistent with what we are finding, but La Nina is not. Once again, it's something for forecasters to be aware of. Maybe that for La Nina phase 7, per lead et al. 2019, is more relevant, although similar looks once again fairly weak, especially in the MGO phase 6. Roadmap from the literature shows much to consider. This is where we're going with, Dylan and I are going with this. We're going to consider the role of the QBO, which influenced the North Pacific jet stream. We're also going to be looking more at more model results as well, see how the model's been doing, several models in fact, versus the reanalysis data. Something I showed before, but I didn't have time to show here today. I also find it kind of interesting. Teleconnections are evolving as the climate changes. So maybe just look at the SST anomaly right now and how warm the oceans are. So what worked in the past may not work now. And I found that if you looked at 20-year periods, 80s and 90s versus the last 20 years, teleconnections are different. So we need to be cautious on using statistical relationships. And references, and I'm done. Go to dinner.
Thanks very much, friends. Any questions? So I have a question. So, I mean, as you know, CPC uses statistical tools, particularly for week 3-4. So a little beyond what you were looking at, but you know, like the multiple linear regression model being a main tool. So that's assuming that you know these the influence of these predictors is linear. But what you're suggesting is that the linear ENSO MJO influence, well, the actual relationship may be nonlinear. So you feel you can rule out the null hypothesis of a linear superposition of ENSO and MJO when it comes to the NAO, or is there some, you think, nonlinearity?
There could be some, I would say, could be some nonlinearity to it. I mean, and you know, that's something that I think could be definitely assessed with this. So yeah, I wouldn't assume linearity to any of this.
Thank you very much. Great. So we're now going to move on to Andrew Badger's talk. This is the scheduled for 4:30, so we're only 4 minutes ahead.
All right, great. So I'm Andrew Badger. I'm at CPC and also at ESSIC. And I'd like to thank my co-authors, Highline Wang, Lee Chu, Minnie Park, Mike Belarge, and Highline Wang. And so today we're going to be talking about flash drought development and the GUESS V12 forecasts. So a little outline for what we're going to talk about. We're going to talk about flash drought identification for a climatological period. We're going to look at 2000 2019. We're going to use the USDM as our truth, as our gold standard, as someone called it yesterday. And we're going to use offline NOMP HR1 using NLDAS2 forcings with 3 different soil moisture-based methods to compare with the USDM. And I'll come back to these methods in a second. Then we're going to look at the meteorology in the development period of these flash drought events. And we're going to look at the model-produced soil moisture that occurs post-development or during development. And then we're going to look at a recent flash drought and the SPI associated with that. So to circle back up, to look at the 3 flash drought methods that we're going to use in comparison to USDM. We're going to use the USDM method. It's from Chen et al. 2019, and it requires a 2+ category degradation in the USDM category. So, you know, D1 to D3 in a 2 to 4 week period. We're going to look at the Mon-Yan method from 2023, and that requires a soil moisture percentile drop from greater than the 40th percentile to less than the 20th percentile, with at least 7 percentile drop per week. And then we're going to look at the soil moisture volatility index, and this is from Osman 2021, and it requires the 1 week running average of the root zone soil moisture to drop below the 3 week running average of the root zone soil moisture, and then also get below the 20th soil moisture percentile. So we have 3 different methods that all are going to be soil moisture based compared to the USDM, and we're going to see how those compare. So this is what we're going to call our first problem, and that's going to be flash drought identification. I was at AGU this year and was in a couple flash drought sessions, and I think every single talk had their own method for identifying a flash drought. So it's a very ambiguous definition of something to define. So if we use the USDM data and we do the 2+ category degradation in a 2 to 4 week period, we get this map here on the top. And you can see we kind of have a hot spot down here in the southern U.S. and we kind of see, some increased activity kind of up through the Still Great Plains. So we see less out in the central in the western U.S., the Great Basin, we see kind of less along like the East Coast. But if we use the 3 soil moisture-based methods, we don't see that same pattern. You kind of see it in Niang, but a hidden feature of this is that the USDA method can also capture something going from a D1 to a D3 or a D2 to a D4, so like a rapid intensification of a drought that is already present. Whereas the Niang method is only capturing development of drought. So it has to go from being a non-drought condition to a drought condition. So even though they look similar, it's kind of, it's maybe not apples and oranges, maybe more like apples and pears. But these two are completely different from the USDA method. So when you're trying to identify a flash drought, this shows that it's already a very difficult task to even just define what a flash drought is. The second problem is that flash drought is a rare occurrence. So if we look at so this is from USDM, this is the same map that's on the previous slide. If you look at the 4 seasons, March, April, May, June, July, August, September, October, November, and December, January, February, you can see that our flash drought development really peaks in JJA. But if we're talking about how often is this happening, if we look annually, it's happening in USDM 0.8% of the time. If we look at JJA, it's happening 1.6% of the time. So we're looking at something that is not occurring very often. So to try to assess the meteorology during these very rare events is going to be a numbers game. It's going to be very tricky. We don't have a lot of sample sizes, and there's really no way around that. Also, if we go back, or if we look at the other methods that were shown on the previous slide, they also have a very rare occurrence, but they don't peak in JJA like the USDM does. They tend to peak in MAM. So looking at how the GESS V12 does during this developmental period. So what we have here is in these larger maps, we have temperature on the left, we have precip on the right. These larger maps are the mean temperature anomaly during the flash drought development phase from our climatological period, so from 2000 to 2019 using USDM. What we have vertically in the smaller maps is GESS V12 week 1, 2, all the way to 5 at the bottom, and the mean anomaly associated with that lead time. So we can see that with temperature, the week 1 forecast during any time that flash drought was developing, we can see a very similar anomaly picture. It does look like maybe the anomaly is not as strong in GESS V12, but we are capturing, warming over most of that region. And you see warming out to week 2. Then once you get to week 3, 4, and 5, it kind of becomes like a mixed bag of temperature. So the interesting thing is that we know that temperature and precip are the main drivers for flash drought development. And the great thing about this instance is like we can have no drought in week 1 of our GESS V12 forecast, and we can have a full-blown flash drought in week 5 of our GESS V12 simulation. So it's an event that can both develop and be present within a single GESS V12 simulation. So not being able to capture the temperature anomaly out beyond 2 weeks is going to prove very hard to get the soil moisture development that you need to identify a flash drought. Looking at precip, we can see week 1 captures the precip deficit that we see in S2, but once we get past week 2, you can kind of see some drying, but then it also kind of becomes a mixed bag. So what our GESS V12 anomalies are telling us compared to S2 is that, maybe 2 weeks out, you can kind of see the drying or the warming, but beyond that, it seems to be a mixed bag, which is disconcerting when it comes to developing a flash drought, something that happens on a 3-week timescale. We're about 1 week short of being able to really capture it. So looking at the error, this is something that I found particularly interesting. So we'll start with the precip on the right. So what we have is the CDF of the mean absolute error, and I broke it down into 3 regimes: when there's no drought, when we have flash drought development, and then when we have flash drought present. And you can see in week 1, you can kind of see that all 3 have a very similar distribution. The developing flash drought is maybe showing a little bit less error early on, and that's just probably because 0 precip in the model, and you have 0 precip in the observations typically in that week 1. So we're going to kind of see a little bit better error there. We're kind of bounded. Whereas when you go to week 5, you can kind of see all 3 lines are together, very similar distribution. We do see the error grow, which is something that we would expect. But when we look at temperature, you can kind of see that we kind of have 3 separate regimes at week 1 between the no drought, developing flash drought, and the flash drought being present. But then when we get to week 5, you can see that all 3 air regimes have shifted to greater air as time goes on, but they've also remained separated. So we found this to be a very interesting result, is that while the error grows, the error in the developing flash drought period tends to grow faster than it does when there's a no drought present or a flash drought present. So when we're talking about being able to forecast something that's happening on like that less than 5-week time period, usually like the 3 to 4 week time period, knowing that your error in the temperature is growing within the model during those time periods is going to make it even trickier to get the associated temperature that you need to develop a flash drought. So now we're going to switch gears to volumetric soil moisture. So volumetric soil moisture is kind of an integrator of the atmosphere. So it responds to both the temperature and precip. So this is the mean anomaly during the flash drought development. And this is the mean anomaly for guess V12 week 1, 2, 3, 4, and 5. And even though we showed that there was little predictability in the temperature and precips really beyond 2 weeks, during the flash drought development period, we can see drying in guess V12 out to weeks 3, sometimes week 4, and even in some instances in week 5. So we are seeing that drying that we need to see in our flash drought identification methods present in our simulations with NOAA when forced with the guess V12 meteorology. But when we look at the error of the volumetric soil moisture, you can see in week 1, all 3 are pretty similar together. There's no separation between the no drought, the developing drought, and the in-flash drought periods. But when we look at the volumetric soil moisture errors in week 5, we see a very similar picture as to what we saw with the temperature in week 5, is that the error between the no drought period, the developing drought period, and the in-flash drought period are separating again. So it does seem that while VSM is showing the correct anomaly at week 5 or out to weeks 3, 4, and 5, the error is still present, and it seems to be being driven by the errors in temperature. But we're going to switch gears a little bit because the U.S. Drought Monitor does not use solely soil moisture. In our work with what we've been doing so far, we've been using a lot of soil moisture-based methods to identify flash drought, but the USDM uses a lot of other inputs such as like SPI, SRI, Palmer drought, SPI. So we're going to look at a recent event that happened on the East Coast. So this is the USDM from June 11th, 18th, June 25th, and July 2nd on the top. And then on the bottom, we have the 2-week change. So this would be, this map would be June 25th minus June 11th, and this would be July 2nd minus July 18th. So what you can see in these maps, you see a lot of drought development occurring along the East Coast, particularly up through like Maryland, Virginia, North Carolina. And you can see that there's a rapid development of flash drought that occurred during that period. So we talked about how we kind of have this a horizon of skill in guess V12 of being 2 weeks or so when we're looking at the anomalies. But when we look at SPI, so this would be the lead at June 5th, you can kind of see that we don't really see a lot of drying along the East Coast. But we look at the lead for June 12th, we can see that there is a severe amount of drying in the SPI, and that anomalous SPI drying lasts for the next 4 weeks. So we can see that if not looking solely at precip, but if we use this, the standardized precipitation index, we can see that the anomalies that you would need to identify a flash drought are still present in the meteorology in guess V12, even though they don't show up necessarily as the typical anomalies do. So in closing, I'm going to start out with flash droughts. Our identification is tricky. I showed you 3 different methods. They all give you 3 different results. So that's something that probably needs to be worked on before we can really identify the drivers in flash drought development. And then capturing the development during these events is hard. They don't happen very often. Over a 20-year period, in some grid cells, you only have flash drought present or developing for maybe 25 to 30 weeks, and some you only had it happening like 3 to 4 weeks. So it's a tricky thing to try to really gauge what is happening with the meteorology. During flash flood development, GESS V12 captures the general temperature anomaly and the precipitation anomaly. So it seems to capture the warming after 2 to 3 weeks. It seems to capture the drying after 2 weeks. And the air and temperature forecast shows increased air during the development period, whereas in the precip, we saw the airs kind of all grow, but they all remain the same, but was the temperature, they kind of separate into these 3 different regimes. And using other meteorological indices like SPI will help identify or capture the flat belt development. And that's something we can do with GESS V12 presently. So with that, I'll take any questions.
Very much talk. Any questions?
Yeah, thanks for the nice talk. So in the session before this, we heard you talk about identifying marine heat waves as sort of coherent connected structures. And so I'm wondering, when you talk about the infrequency of these flash droughts on a grid type basis, I don't know if you saw the talk I'm referring to. Do you think there might be some benefit to perhaps identifying flash droughts as a regional phenomenon? I don't know if that would increase the frequency.
So I did not see that talk, but what I did hear was I actually did filter the flash droughts to be a coherent structure in both time and space. So it's not just a grid cell, a single grid cell somewhere flipping onto a flash drought and then flipping off from a flash drought. It's a coherent structure of at least 25 grid cells together.
Okay. Thank you.
Hi, Andrew. I had a question about this flash drought identification is tricky. Do you think that has something to do with physical mechanisms or way in which you're defining a flash drought? You know that there are certain features that get pinged if you're moving from if you're doing a 2 week, if you're doing a two degradation, 2 class degradation in 2 week period, versus if you're just already at class D0 going to class D1, I guess. Right, like, I mean, because there are different factors that are in play when you're in D0, D1, D3, so on and forth. So moving even further deeper into that seems like there's some physical things that are happening there versus in the version.
Mm-hmm.
So do you think that's part of it? Yeah.
So if I'm understanding, like the differences between like the USDM versus like the other methods, why like that might be.
Yeah, there's physical things happening.
Yeah. Well, I think we were looking at the 2022 flash drought, and there's kind of 3 areas of development in the 2022 flash drought. There's a southern area that develops early, and then there's an area to the northeast of that that develops a little bit later, and there's an area to the northwest of that where the USDM shows no flash drought development, and these 3 methods all show flash drought development. And when you look at the USDM through time, you know, like the kind of chart they show, like where it's like the area, the integral of the amount of for each category, the USDM kind of remains it shows that there's drought present. It just doesn't show that them changing their categories as often as the model would change, like the soil moisture. So when the soil moisture is kind of dry already, a very little change can change your soil moisture percentile from being like 25 to 12. And it's not a very large change in soil moisture. So that kind of anecdotal knowledge is fed into the USDM by their authors.
Thank you, Andrew. Nice presentation. You said that the error growth during the flash drought events are larger than the errors for the other outside of these events. I wonder if that's because it's a sample size issue, because we have such a small sample for these events, and when we look at the error.
Well, I thought about that, and if we did like the math, we have like 4,000 grid points, and we have 1,000 weeks of data, and so then if we look at just a quarter of that for JJA, and like if we're saying like 1.5% is in developing flash drought, we're still at about 14,000 points. So I don't think, as those samples are certainly not as large as the other two, as of the in-flash drought or the no drought time period, but it's not like those plots were made with, 20, 50 points. I think there's a large enough sample size to kind of see that if we had more data, that I think that these lines might converge a little bit, but I still think we'd probably see a separation.
Great, thank you.
Yeah.
All right, and we're going to move on to our final talk of the session by Erik Swenson.
That was it. All right, well, thanks for sticking around here. This is some work on UFS reforecasts I did with Ben Cash, also with Julian, neglected him on the slide here. So our motivation is the ultimate motivation to improve S2S prediction skill. So we want to look at potential sources of bias by motivated by looking at extreme precipitation in the wintertime over the U.S. We'll compare to some observational products, just look at the relationships with the large scale circulation. Now, I also looked at some other variables like SST, but in the interest of time, collecting that. So we ran UFS P8 at 27 kilometer resolution. And this is nice. We actually ran it out to 9 months. I'm just looking at the first 5 months, but you get to see what happens after a month, right? And it's a same 7-year period, but we have some ensembles. So it's a good amount of data, maybe 30, 40 years total. We'll be comparing to URA 5, specifically looking at the 500 hectopascal geopotential height, and then CPC unified precip. Well, just defining heavy precip is when the occurrence when it exceeds the 95th percentile, at each grid point. We did do some filtering, 5-day running mean with Z500 to kind of pick up some more low frequency a little bit. And then just subtracting a smooth seasonal cycle. There's not a lot of years, but it's a nice way to do that. Just look at anomalies. And also I'm looking at previous data, URA 5, back to 1980 as well. So we did truncated the Z500 to the first 20 EOS, which is most of the variance. Then did some lead lag relationships. I think I'm just showing simultaneous. To explain, a heavy precip at each grid point, I use logistic regression. I did try some more nonlinear classification techniques, but maybe improve the skill when there's already a lot of skill, but overall it seemed to actually degrade it. A little harder to understand too. So we'll be able to look at some actual regression patterns, which is nice. And we have, we're using, a big chunk of the data and then verifying over 7 independent years for both observed and the model. So if you look at the actual PDFs of precip, here in the top panels showing just percent of time it's not raining, right? Or snowing or precip. So percent of dry days, and you see they look on the left and the right. Left is observed and the right is UFS. So you have the common problem that it's always raining a little bit, the drizzle bias. But if we look at the other tail, 95th percentile, these bottom plots, it looks pretty good to me. The actual values, the geographical variation. So we have the, over the Rockies on around 3 millimeters per day, and then reaching up to 30. especially on the West Coast, which is more of the focus of this talk. And also climatological mean precip look pretty reasonable in the model. Again, this is winter time, just October to February, actually. So here, the skill from using Z500 to try to predict extreme precip occurrence. These are the prior skill score map, each grade point. So you see it's most skillful, or at least circulation explains, variations in extreme rainfall most on the West Coast, as we would expect. And that is reproduced in UFS. And if here I could compare these skill maps to just a climatological forecast. It's actually showing up pretty bad here, but you can see it, we are getting some skill, even though values are only going up to about 0.3. And it does seem to have too strong of an association with the circulation over like Southern California, the plains, and maybe a little too weak on the East Coast, which does show up in the other results. That was maybe one of the key differences, but otherwise looks pretty reasonable. And then if we look, I'm making a prediction at each grid point. So if I actually take the regression patterns associated with extreme precip at each grid point and try to clump them together, just cluster analysis of the regression patterns. So you can, and then I look and see where each cluster is. You do get some agreement that you would expect. This is a large scale circulation. So over the Pacific Northwest, tend to have this pattern on the lower left. And then that is reproduced pretty well in UFS. And here, if you look at like the Southwest pattern, looks quite similar, and even some anomalies upstream and downstream. And then you get more of a wave train to produce extreme precip on the East Coast here. So this, maybe not a surprise, but also the variance of these patterns in the reforecast seems pretty realistic. So that was encouraging. And I did look at other variables like moisture flux, SST, which I might comment on if there's time. I think maybe I'm going pretty fast, but if we look at also just simultaneous to going back 10 days prior to the heavy precip, just look at a few grid points. You can see like here in the blue is a point near Idaho, and it's tend to have more skill even back to 10 days with climatological in the gray here. And then if we look Southern California, the model is quite different. Sorry, the dashed lines are the UFS, and the solid lines are with ERA 5, observed precip. So in Southern California, you see that it's much more of an association with this big trough than you might expect. Maybe that has to do with, there are other reasons, why getting heavy precip in nature. And then it's association's too weak in the model. If you look at a grid point out east, like over Maine, it's there, you get the same pattern, but it's not as strong, not as much explained. That's actually all I have. Maybe if I have a little time, I might show an SST result. But yeah, UFS did a pretty good job reproducing the association between extreme precip and circulation. There were some differences, in the plains and the Southwest, but overall it was pretty good. And also the PDF, the actual values the 95th percentile. And I did want to, the ongoing work is to actually link this to the errors like in the first month. So I think that was too fresh to show, you know. But and then if you look at SST, for instance, all you can really do is look at the leading PC, which is, if you include the tropics, that's ENSO. And you can get a little skill, you know, from ENSO to explain extreme precip, but at least over the 7-year period, ENSO is pretty strong in the UFS compared to, you know, observed. And so that might have some implications on heavy precip, definitely. And also the imprint on the extratropical SST seemed pretty strong. And so imprint. But anyways, if there are any questions, thanks.
Erik, are there any questions? Yeah, I have a question. So, maybe this is covered in I missed it, but based on what you've shown, let's say you had to make prediction for precipitation using the UFS right now for, I don't know, first, you know, within 10 days or something. So, would you recommend using the direct precip output from the UFS, or looking at the predicted 500 millibar height and then, you know, then making using logistic regression from the predicted heights to the extreme precip? Is it clear that one would be better than the other?
Oh, yeah, I did look at that, and it's much more skillful. You just use what Z500 would tell you.
Oh, yeah, okay.
I mean, it's at every grid point, you know, the same day are we getting, you know, extreme precip. That's tough, right? I'm a little new to looking at extreme precip, but, you know, definitely constraining it like this improves the skill.
Very nice. Okay, well, I guess that will conclude our session. So,
Sorry, just one real quick announcement. We are now done with post-success students. If you have not voted on anything, we are looking for votes for our early career recognition award that we'll be giving out tomorrow. So please take a look at that. Also, wrapping up here right now, but we will be heading over to Denizens. We're scheduled for 6 o'clock. We'll probably walk at 5:30. I've got 30 people registered, but you're all welcome to come over, hang out, get some food, have a drink, continue the discussions. And as usual, thank you all for participation.